work on this paper, Graph Attention Network. Why are you so well known for this paper? What is the big novelty there? Do you think that people were accepted into DeepMind? Are the people special? Are they all normal people? What do you think that they have that others may not have?
I mean, to this day, I still have imposter syndrome, to be honest. But, casting that aside, they are all really special people, but they are really special in different ways. If you want to know more about transformer positional encodings, try to dive deep into the code for them and figure out why are they built the way they're built, what are ways in which the code could be made faster, more reliable, what are the ways in which you could maybe modify them to get different outcomes, right? So that's one way. Get really comfortable with implementations. Arguably, all of these 20% projects were the projects at DeepMind that I'm maybe most well known for externally. So first, the work we've done with Google Maps on improving their ETA algorithm.
I'm a big football fan, support a bit more Tottenham than Liverpool. How did this idea of improving corner kicks came up, and then how did you use AI to solve this applied problem?
One thing that was really missing for a lot of the people I've spoken to is, I wouldn't even call it initiative, but just confidence. I mean, if you never fail, you have failed, right?
All right. Hello, everyone, and welcome to the AI Stories podcast. I'm Leiser. I'm a senior data scientist, and I will be your host. So today, super exciting episode. We've got Petar Veličković, who is a staff research scientist at Google DeepMind and an affiliate lecturer at University of Cambridge. So Petar has been working at DeepMind for around 6 years. He specialized in geometric deep learning and GraphML, and he has been in charge of a couple of great projects like improving the ETA algorithm of Google Maps, or more recently collaborated with Liverpool FC to build an AI assistant that can help and advise coaches on corner kicks. Before joining DeepMind, Petar had a bunch of internships, and he also got a PhD in machine learning and bioinformatics at the University of Cambridge, and a Master of Computer Science from Cambridge as well. So this is a very exciting episode as we're kicking off season 4 of AI Stories. If you enjoy our conversation, please subscribe to the AI Stories YouTube channel, comment, share, and leave a 5-star review. All right, so let's start now. Hi, Petar. Hope things are going well for you. Very excited to have you here today. First thing I want to know is, how did you get into this world of AI and machine learning? How did you get into the field?
First of all, hi, Neil. Thank you very much for having me. And it is a pleasure to be speaking to you and all of your listeners today. I hope that you will enjoy the conversation we'll have and hopefully get some interesting insights out of it. My road to AI was actually quite an unexpected one, in the sense that I was always fascinated by computer science as a field, but I never saw myself as becoming a researcher, much less an artificial intelligence researcher. In fact, what originally brought me into the world of computer science was competitive programming, which itself includes classical algorithms, data structures, things like that. And I've basically oriented most of my undergraduate education towards specializing in those areas. And my kind of target was to become a software engineer. And this was something that was a big goal for me. And I actually ended up doing a software engineering internship at the end of my first year of undergrad. And I realized that actually I did not find the job of a software engineer to be the right one for me. I just did not find the experience to align with my interests and what I want to push for. So I spent the next few years basically, wandering around, trying lots of different things. I worked a little bit in hardware and FPGAs. I worked a little bit in finance. And my thought process was, okay, maybe I will complete a master's in computer science and then find some interesting applied job to work on. What kind of changed things around for me was my third year undergraduate project with Professor Pietro Leo at Cambridge, which was a bioinformatics project. So I basically wanted to do a project in bioinformatics because, as I've mentioned before, like my initial passions were algorithms and data structures. And I knew that bioinformatics was an applied field that was full of classical algorithms. So I thought, okay, if I do a project in this area, I'll get to do something applied and useful while also playing to my strengths and doing something I'm passionate about. But at our very first meeting, my advisor told me that basically, this is all nice and bioinformatics is indeed full of classical algorithms. But if you want to kind of do the kinds of things that a modern bioinformatician is doing today, you should probably learn machine learning. Mm-hmm. And it was that inspiration that initially pushed me to kind of self-study basic concepts of machine learning and deep learning. And I ended up both really enjoying learning about the area, and also I enjoyed kind of the day-to-day work of building an AI system, training it on data and testing out its predictions. So eventually I was convinced to just jump right on board. My supervisor had some funding available, and I started a PhD at Cambridge the next year, which basically kickstarted my road in artificial intelligence.
Great, nice story. And so I mentioned that you're really like GraphML, you're a specialist in GraphML and geometric deep learning. So how did you get into that then? Was it during your bioinformatics project? Was it more during your PhD? How did this happen?
Yeah, during my bioinformatics project, there was no deep learning involved. I actually knew nothing about how to build and train a neural network. It was all hidden Markov models at the time, actually. Actually, at the start of my PhD, I still did not expect I would be working on deep learning. I didn't know much about it anyway. But I started noticing the trends around that time we're gravitating towards the use of neural networks. And I basically ended up self-studying on Coursera and Udemy basics of deep learning with Keras at the time. That was kind of one of the popular entry-level frameworks. And almost all of the tutorials, as those of you who were around back then in the field probably know, most of the tutorials were to do with computer vision and classifying images on smaller scale data sets. So just as a simple corollary of what I was working on, I ended up training CNNs to begin with and focusing on vision data sets. And some of the first publications I've done were in that area. So I initially did not particularly have an orientation towards graphs. And in fact, while graph machine learning was a thing at the time, when I started my PhD in 2015, I would say that it did not really start to blow up until late 2016, mid 2017. And that happened to be the time when I started out my internship at MILA, the Artificial Intelligence Institute in Montreal. I was working with Joshua Bengio and Adriana Romero at the time. And basically, that was like that summer of 2017 was a really crazy year in artificial intelligence generally. Once again, for those of you who were around back then, you will probably know that this was the time when the Transformer paper hit the archive. So for the first time, I was doing my internship at Mila when the Transformer paper first came out. Also, there's already been some traction gathering on the graph neural network front because the graph convolution network model from Thomas Kiff and Max Welling came out a few months before. And that paper really amplified the drive of people to join in on the action and do modeling things in the graph representation learning space. So when I had my first meeting with Joshua, when I came at Mila, he basically said that he's been reading about these graph machine learning models recently, and he's been really interested in them. And then also there's been this Transformer paper, which reignited the public's interest in attention, which a lot of the earlier papers that kind of really popularized the use of attention mechanisms before transformers came out of Mila. So they had a pretty good expertise in this area. So Joshua had this cool idea. What if we take the concepts from, these attentional mechanisms and transformers and see if we can use them to build better graph machine learning models? And this is what led us to create what later became known as the Graph Attention Network, which is a piece of research that I guess to this day I'm still best known for. So yeah, it was basically, I was heavily steered towards studying graphs, but then I both really enjoyed working on it, and I realized how working on arbitrary structures like graphs can be related to all of this algorithmic and data structural stuff that brought me into the field and made me passionate about it. So once I was already in graph representation learning, it was not hard to stay there because it was an area that felt very comfortable for me.
And so you work on this paper, Graph Attention Network. I'm not an expert in GraphML, but what is the big novelty here? Is it that you basically combine classical GraphML algorithms with the attention mechanism and empower them? Why are you so well known for this paper? What is the big novelty there?
I would say I think the two questions you asked are a little bit in contradiction with each other, because I don't think the paper had particularly huge novelties, but it just became very popular as a base model, as a baseline, and it's seen lots of applications inside, natural sciences and so on. But okay, to actually address your question, the novelty in this work was mainly the fact that you could take an attentional mechanism and just deploy it on top of an arbitrary graph structure. So we had a particular input graph that we wanted to do some predictions over, and this graph has nodes, which are similar to tokens in a language model. And also it has some edges. So there are some connections between the nodes that you are aware of. For example, one standard data set at the time was the Cora data set, which is a data set of papers. So every node is a scientific paper. And the edge between two papers means that there is a citation. So this paper cites the other paper. And the task is to predict the topic of each paper, right? So obviously you can learn something from the text of the paper itself, but you can learn a lot more if you contextualize it in the related work section of that paper, right? So that way you can leverage the graph to get better predictions. And previously, I mentioned the GCN paper. That was kind of the most popular model at the time. And that model, I would say also partly because of the very large simplicity of the tasks at the time, it was very easy to overfit on them. So what the GCN paper did is a relatively simple sort of averaging procedure. It's not quite a simple average, but it's maybe a few steps beyond that, where every node effectively looks at every neighbor and treats them in a way that's kind of proportional to the size of the neighborhood of that node and the neighbor. So it's kind of a slightly more fancy average across all of your neighbors. And I must stress that for some applications of graph machine learning, especially in like social networks, this is a perfect thing to do. Like, I can tell a lot about my own behavior if you look at the average behavior of all of my friends on a social network. And for many topics, that is very much true, right? And the simple averages are also much more amenable to a scalable implementation. So industrially, this model is still super powerful and super popular. However, this is not the case for all graph structures we have, right? So for example, I'm very active on X, formerly Twitter, and I write a lot of posts, a lot of retweets and stuff like that. Sometimes I will repost an article because I really agree with it. Sometimes I will repost an article because I fundamentally disagree with it. And you should not treat those two edges the same. You should not average across the two to get my opinions, right? So I guess my main point there is it will be good to have a mechanism that can selectively choose which neighbors in your graph structure are most important. And that just happens to be what the attention mechanism is good at in principle, right? So that is kind of the main idea. I must stress that, this paper was developed around the same time when the transformer paper hit the archive. These works were almost concurrent in terms of their development. So that general time, mid-2017, was generally a melting pot of some really cool applications of attention. And our work just happened to be one of the first times it was done on graphs.
Nice. And I guess you showed that, GraphML with attention could lead to better results in a couple of use cases.
Yeah, I mean, I think there's also a point to be made about the middle ground effect. So you have GCNs on one side, which are simple but a bit easier to scale. You also had these message passing neural networks, which also predated the graph attention network. And they did something more expressive. So they did not compute, like attention would compute a weighted combination of all the neighbors. Here, you just let each neighbor send you a message, and that message is a vector. You have no kind of easy interpretation for what those messages are, and you just aggregate them together, right? So this is more powerful. This can simulate attention if you choose the right kind of message function. However, it's basically a trade-off, right? Because it is a more theoretically powerful model, but it's harder to scale because now you have to store vectors per edge rather than per node. Every message is a vector on an edge. And also it's harder to interpret, easier to overfit, these kinds of things. So attention kind of strikes a nice middle ground where you're allowed some learnable control over how much you value each neighbor through the attention coefficient. But it's still actually, once you compute the coefficient, it's still remarkably easy to scale. So it gives you a little bit more power than the GCN, but it doesn't sacrifice that by being tragically slower. And also, because you have attention coefficients, it can lead to some potential interpretability gains because you can look at the coefficients and sort of understand what is the network finding important when driving different decisions, right? So that, I think that kind of connection was part of the reason why it became so popular, because it was a way to get a powerful model which doesn't scale too badly with size. And because of the interpretability qualities, I have seen a lot of times it was used in like a biological or chemical setting where people would analyze the attention coefficients and actually try to make sense of what's happening. So I'd say it just strikes a very nice sweet spot. And actually, I think this sweet spot might be hinting also at why transformers ended up being such a popular model overall, because like the attention mechanism gives you just that extra bit of expressive power kick that you can now model complex interactions between tokens, while at the same time the operation is something you can scale up very easily if you have the right kind of hardware. So that's kind of that's I would say part of the reason why it's been so successful.
So you do your PhD, you write this paper on graph attention networks and other papers as well. And then after that, I think not too long after, you joined DeepMind as a research scientist. So, well, first question, how do you get into DeepMind? It's probably the top job for AI research. So how do you get into it? What was your experience there?
Right. So, yeah, I did actually join DeepMind relatively shortly after submitting my PhD. In retrospect, I would have probably loved to have taken some, gap year or some downtime like that. But basically, because of visa constraints, I had to do this now, or, risk being in a weird situation with like UK immigration. So I was kind of pushed into the situation of starting work early. But it was a really interesting process getting to DeepMind at the time. Our interviewing is not like that anymore. It used to be a little bit more, I guess, challenging, and it took place over a longer period of time. But I mean, the essence of how to get to DeepMind is still more or less the same. So I like to think that to a large extent, you can relate DeepMind to a sort of university environment, especially in its more foundation research aspects. So you can imagine basically speaking to someone who is leading a team at Google DeepMind, and they might have some openings, and you could write them an email the same way you would write an email to a professor if you wanted to do a PhD with them, right? So you would share about some of your interests, some of your research, get talking a little bit about potential kind of joint ideas. And if there is interest and if there is an opening, this could lead to a set of interviews, right? And then the interviews themselves are a mixture of technical engineering and research interviews where you get to show off your coding skills on one side and your code understanding skills especially, while at the same time showing how well you understand basic research concepts and kind of fundamental undergraduate level materials in different parts of mathematics, statistics, machine learning, and computer science. And At the end, you have a bunch of these research chats, which are basically, I mean, they can be anything, right? Depending on who's your interviewer, that chat might go in a wide variety of directions. But usually it's just a relaxed conversation of about 30 minutes about some work you've done before. What are some specifics that make the work popular or useful? How would it be applicable to some settings that the paper doesn't cover? Just trying to get a feel for the researchability. And if you're applying for a full-time position, so if you're not kind of converting from an internship, which I didn't do DeepMind internships beforehand, you also have to give a talk. So it's not too different to like how when you're applying to an academic position, you have to give a job talk and you have to talk to some people in the department. On that side, it's very similar. I would say maybe the emphasis on like coding capabilities is something that you wouldn't always expect to get in a postdoc application, as far as I'm aware.
And so do you think that people who are accepted into DeepMind have something in common? Are the people special? Are they all normal people? It's such a competitive field. Like, what do you think that they have that others may not have?
I mean, to this day, I still have imposter syndrome, to be honest. So I don't particularly think that I am very special in this regard. But, casting that aside, I would like to say that in GDM, I would say the people I work with day to day and just, the people I get a chance to interact with, they're all really special people, but they are really special in different ways. I think this is really important. Like GDM is a company that really celebrates the diversity of skill sets that different people can bring to the table. So we have people working at GDM who are, top tier AI professors for decades. So they've accumulated a lot of knowledge and a lot of perspective about how the field is developed over a very long period of time. While at the same time we have people who are fresh out of their undergraduate degrees, starting out as research engineers or software engineers, like having this unlimited passion and just a drive to build fun systems and to learn and to grow and just develop. So it's everybody brings a different skill to the table. And I feel like it's this connection mixture of both research-oriented, engineering-oriented, creative, applied work that makes us a great place to be. And at least what makes me feel very overjoyed to go to work every morning. So it's really a little bit of everything. But nobody is an absolute master of every single trade. I think all of us bring different skills to the table, and it's the synergy of those skills that really make DeepMind a great place to be.
And if I want to apply to DeepMind, let's say in a year, what do you advise me to do?
So it depends a lot on what position you would be applying for, I would say. So there's obviously, as I said, the more scientific positions, there's more engineering positions, there's more product-focused positions. I mean, you can always look at our careers page that's always up to date. You can see what we have available in which teams and on what levels. I can tell you a little bit about how it is for research scientists, because this is the track that kind of I've started out in. And that is kind of our standard research track. So that one typically expects you to have a PhD degree or to be close to finishing a PhD degree or to have done a PhD equivalent level of work. You need to convince your interviewers and your committee that that you've done something that's equivalent to a PhD or close enough to a PhD. Generally, it's expected that you have a strong research skills. So you are supposed to show that you've had a good level of publications in artificial intelligence venues, preferably. So, one piece of advice there would be to try to kind of push out some more works at different research venues, and also to strengthen a bit the foundations. So to understand kind of undergraduate level things in important areas of math, stats, machine learning, computer science. I would say those are really key skills if you want to go for a research scientist position. Research engineer positions are a bit more flexible because they don't require a PhD. You can go there with a bachelor's or a master's. So most of the people that reach out to me for advice for GDM are in this category, actually, if they don't even know where to begin. So that's kind of to dispel the first myth. You can work at GDM without a PhD. It's just not going to be on the research scientist track. It will be on the research engineering track. And to be honest, in modern AI, the line between scientist and engineer is so blurry that you can often find a scientist like myself working a lot on engineering stuff, and you can find a lot of research engineers working a lot on scientific projects. So, like the line is.
What's the difference between the two, actually?
So basically, it's that once again, like the line is super blurry, but the main difference, I would say, at least kind of aspirationally, is that research scientists are great at organizing, managing, and executing research. So they can be kind of expected to kind of lead autonomously or in a team different research projects relevant to the development of artificial intelligence or its applications in the sciences or industry, and just be able to deliver quality bits of research that lead to kind of demonstrable, useful conclusions, right? These conclusions then might lead to publications. I'm personally involved in a more foundational research aspect of the company. So for me, one of the main things I do is publish my work at conferences, give talks. I also do a bit of teaching at Cambridge, as mentioned. So but a scientist could also end up publishing a lot of internal technical reports and not necessarily going to conferences. It really depends on what is the modality of research that works best for you and works best for the part of organization you're in. But it's all about the execution and the ability to kind of flexibly adapt to challenging environments and solve problems that we haven't thought about before in a conceptual level. That would be maybe the main distinctive quality. Whereas research engineers tend to be, as we call, great experimentalists. So actually, a lot of our research engineers also have PhDs, by the way. They'll just have PhDs in maybe more adjacent areas like mathematics, physics, or other STEM topics. So a lot of them will be really good researchers already. Others might be fresh out of university, like undergrad or master's computer science, and not yet with research skills. But the main idea of what a research engineer does is that you're also working a lot to advance the research in these areas, but you are doing it in a more experimentally driven way. So it's by setting up experiments, writing up infrastructure, and kind of making sure that everything works in a scalable manner and is driven to execution in the best possible way. So, as I said, the line gets blurry. Like when you're a scientist leading a project to demonstrate some concept, very often this will involve writing some code. And the more scaled up that code is, the more kind of engineering heavy the work is. And as I said, I find myself doing engineering oriented things all the time. Similarly, when a research engineer wants to demonstrate a new result, they might arrive at this result through pure engineering methods, but at some point it becomes science, and the engineer might assume the role of a scientist if they want to, for example, publish the work somewhere. So, yeah, like I don't think this necessarily gave you a very sharp answer, but that's working as intended. We are not like siloing people into different categories, and there's no way for someone to do anything outside of that category. We're actually quite flexible in the kind of work that you can do day to day.
Yeah, no, but I think the distinction makes sense. I mean, research scientists are more focused on research and developing new things or thinking about how to develop new things, whereas maybe research engineers are more towards implementation and coding things and proving that the algorithm or what the research scientist thinks about a new algorithm, whether it's working or not, or whether it's improving the field or not.
I mean, I would almost completely agree with you. I would just say it doesn't have to be a research scientist who's driving the idea, right? It can also be a research engineer driving the idea. That's totally accepted and totally welcome in the company. I would say that, so it's really about, conceptually, where do you see yourself more? And generally, if you want to be in a position where you're kind of independently, flexibly executing lots of research, you kind of, to show that you're capable of that, you need to do a PhD's level of work. Like that's kind of the way in which that is demonstrated, that you have that capability. So just, I want to circle back to the question about advice, because for research engineers, there is a slightly different set of advice I would give, especially if it's someone who's like still in their undergrad or starting their master's in computer science. I would say the key things are to get really comfortable with the modern machine learning trends and the concepts, and especially how they're implemented. So this doesn't have to mean you need to understand the whole AI stack top to bottom without any, gaps. Nobody does that. But you should identify certain things that you're really passionate about and just go in depth, right? So try to understand, I don't know, if you want to know more about transformer positional encodings, try to dive deep into the code for them and figure out why are they built the way they're built, what are ways in which the code could be made faster, more reliable, what are the ways in which you could maybe modify them to get different outcomes, right? So that's one way. Get really comfortable with implementations, build a portfolio on GitHub or something similar. That's also really useful to have. And it would be ideal if you also make some tiny excursions into the world of research. So you can take some of these papers that you find interesting, digest their code, and then, propose some small changes to the code, see what happens. And usually when you get one or two experiments like that, that's often enough to publish at a top tier workshop, like a workshop at NeurIPS or ICML or something like this. Like, typically, this is maybe one of the best kept secrets in academia, which is actually quite useful, that if you publish your work inside these workshop events, it's much easier to get in than to publish at the conference itself, but it still gets a ton of exposure. And now you have a seal of approval in like a published piece of work that basically says, this person is not only excited about research, but this person is capable of delivering a research result. So these things taken all together have led to several people successfully landing research engineering jobs at DeepMind. So it's a tried and tested strategy to some extent.
I want to now move back a bit to your career and the projects that you worked on. I mentioned you worked at DeepMind for the past 6 years, roughly. Mm-hmm. How did your work evolve over those past years, from when you started until what you're doing today? How did you evolve throughout your career?
Right. So, I would say that it's an interesting story. So I started out actually thinking I would work on continual learning. It was a problem that I was quite fascinated by at the time. For those who are unaware, continual learning is basically having an AI system that constantly ingests new information without forgetting old information, and like being able to act both on present and past data as it continuously arrives. This was a huge problem in neural networks at the time because they would suffer from what is known as catastrophic forgetting, where the new incoming information would just completely wipe out the old information, right? So I tried to work on that for some months, and I think I had interesting ideas, but what basically came about it was that we just did not have the right data sets for the kind of research that I wanted to do at the time. So I actually executed a pretty sharp pivot after 5 or 6 months at the company, and I moved into this area, which now we call neural algorithmic reasoning. This is my main area of research today. And it deals with trying to build AI systems that are better at reasoning. So specifically better at robust reasoning. So this might not be the same kind of reasoning you see if you read around X and LinkedIn about results relating to reasoning of AI systems. Here, I don't mean performance metrics on a reasoning benchmark. I mean capability to truly internalize a reasoning procedure. So, like, if your model has truly learned how to multiply, it should be able to gracefully multiply any pair of numbers without spewing out absolute nonsense. And this kind of robustness is something that I think modern systems all collectively lack. Like, they achieve really cool results on individual sets of problems you pose them, but then it's so easy to just rewrite the question a little bit or change what the input parameters are, and the models completely get confused. So it's something that I would very much like to improve. And I initially worked on this as a kind of pure passion project because initially it was all about taking these graph neural networks and seeing how well they can execute classical algorithms, which, if you remember the story at the beginning, it's me coming full circle back to the classical algorithms and data structures that initially drove me into computer science. So that's one of the parts I really love about my day-to-day research nowadays, is that I get to work on something that's, my teenage passion, sort of, and also something that could make a big impact in how AI systems are designed today. And that, I kind of made that pivot 6 months in, and to this day, this is still my main direction of research. So neural algorithmic reasoning is really the stuff I'm most interested in. And that's where I spend most of my fundamental research time on. What has happened over the years, obviously, is I have refined what the targets and the objectives of the efforts are, such that it leads to outcomes and outputs that are actually useful. So, for example, today we do a lot of efforts studying how well can language models deal with these kinds of problems. spoiler alert, they cannot deal with them that well. And actually, graph neural networks are dealing with these kinds of problems much better than language models. So part of what we're trying to do now is see what was it that made graph neural networks so good at these problems, and can we maybe take some parts of what they're doing and make language models have access to that. So that's kind of the flavor of what we're doing, but it's still the same fundamental kinds of questions I've been asking from the beginning. I'm just now posing them in a slightly different realm. And another thing that I've done over the years at DeepMind is I've learned the value of having a good research portfolio. So you should. I think it's always good to have one project that's like your real pet project, thing you're really pushing for and trying to maximize and showing your full focus on. But then at the same time, every research project will frustrate you at one point or another, and I find it to be really useful when you hit those kinds of frustrating points to have a different research project to kind of direct your mind on. And I find that, at least for me personally, I know that there are some people who very nicely operate in the regime of full 100% focus on something. I'm just not one of those people. I've tried many times, it never worked out for me. So what I've done is I always try to have a 20% project on the side, which I put my time in 1 day a week, which is just something really exciting, not something necessarily related to my core area of research, though I've always been able to apply some of my expertise in these projects and just, try to make a difference on some important scientific or applied problem where my expertise could be useful. And this led to, arguably, all of these 20% projects were the projects at DeepMind that I'm maybe most well known for externally. So first, the work we've done with Google Maps on improving their ETA algorithm. That was one of the 20% projects for me. Then the work we've done with mathematicians. That was one of the first, if not the first result where artificial intelligence helped a mathematician derive a top tier result that was published in a top tier mathematical journal. That work ended up actually on the cover of Nature, which is the most prestigious journal for science in 2021. And that was also a 20% project for me. Started during the pandemic, actually. And most recently, as you mentioned, the collaboration we've done with Liverpool in applying AI for sports and specifically AI for football analytics. Once again, a project I've done in a 20% capacity, but where I've gotten quite significantly involved. And eventually, it became a pretty successful output as well.
Yeah, I'm like you. I really like to, I don't like to focus 100% of something. You shouldn't have like lots of small projects and like do 10 projects at 10%, but like one big project at 80% and another one at 20%. I think that's great because, as you mentioned, you often get tired on your main projects. And so it's nice to switch to something else. You're super excited to work on this 20% project. So you're going to make lots of progress. And then when you come back to this big 80% project, sometimes you get new ideas, you get a bit refreshed, and you get excited again to work on it. So I think it's nice to have at least two different projects. Yeah, it's a fine line. Like, not to we shouldn't have too many projects, otherwise you do a bit of everything and you don't make any progress. But yeah, having 2-3 projects, I think that's a great thing to do.
It took a long time for me to learn how to say no to people. I will just say that much. But it was, now I've sort of nicely settled on this idea that there is the one thing that I'm working on right now. And in a place like DeepMind, it's very easy to have fear of missing out. There's so many fantastic applied projects happening at any point in time. So, I've just learned to suppress that over time.
I'm keen to dig a bit more into one or two of those applied projects because I think that shows a great, how AI can be applied and impacts the real world. Maybe first on the Google Map ETA algorithm. Yeah, do you want to give a brief intro of where were you at when you started the project? What did you implemented? How did the algorithm get better? Is it still used today? Yeah, lots of questions, but keen for you to dive into it.
Sure. So in this case, it was a fortunate positioning that led to me being involved on this because at the time, like, graph neural networks were still one of the main things I was working on. And within Google DeepMind, we had an effort focused on graph machine learning. And I was part of that effort. And obviously, it had lots of scientific directions, but it also had an applied direction. And there were some folks in what was DeepMind Applied at the time that were really trying to see if this technology can be applicable in Google products, because the belief is Google has lots of graphs. Let's try to make sense of them and use them better with these models. And Maps was identified as a pretty solid target for this because there is a very nice graph structure. And at least at the time, it wasn't really being used by the Maps algorithm. So the Maps algorithm, effectively, the ETA problem is given point A and point B and the route that connects them. Try to predict what is going to be the travel time on that route given a particular starting time, right? So how long will it take me to travel from A to B? And then once you have a predictor like that, then there's a simple heuristic that kind of proposes a few candidate paths. And then you can score them and rank them given this time estimate and present them to the user. So when you're using the Google Maps app, you open it up, you say, I want to travel from A to B. You get a bunch of possible paths rated by time. That time estimate comes from the model that we have developed. And I should stress that this is a really important service, not just for, everyday users of the Google Maps app, but also for the many applications and services using the Google Maps API to serve the best outcomes for their users. So, for example, food delivery companies, rideshare companies, many of them rely entirely or in part on the Google Maps API to serve predictions to their customers. When will their vehicle arrive? When will their food arrive? So really, this is a technology that hits billions of users every single day, right? It's a really important prediction problem. I would say that from this perspective, it's also important to think about not just how powerful the system is, so how accurate is the prediction versus how long you've actually traveled, but also you need to make sure that it's highly available. And this is one of the things that it was kind of a great paradigm shift for me as I stepped out of kind of the research land into the more applied land, that suddenly it's not that important which method achieves the highest accuracy. Like if I get a certain amount of small percentage points of accuracy improvements on predicting travel times, if this means I cannot serve a billion people anymore efficiently, it's not going to be deployed. Like you need this system to be highly available. That's more important than being completely precisely accurate, right? So we really had to try to fine line. But we did believe that there was something to be gained by analyzing the whole graph structure of the road network, because while you have a particular route that's being proposed, there are also roads piping into that route and traffic that could be coming into that route and causing issues. Those issues you might not see immediately, right? The previous system kind of leaned more on what are the current speeds of cars in traffic rather than what will happen in the future. But you might be aware that, for example, soon it will be 5 p.m. or 6 p.m. and it will be the end of working hours. Everybody's going to sit in their cars and the center of the town is going to be completely congested, right? So with a system like this, that's both topologically mindful of which edges are going to be coming into your route and also mindful of when certain rush hour conditions might happen, we were actually able to predict a lot better in certain cities than the old Google Maps baseline, the accuracy of travel time predictions. And in some particularly challenging cities, one of them, for example, is Sydney in Australia, we had a relative improvement of 40% and above, which means for all the cases where Google Maps was very wrong, for example, maybe 10 minutes wrong or something or above, 40% of those cases are now correctly classified using the new baseline. That's what the 40% relative improvement means. And that was pretty significant. So this was something that we have been able to deploy inside Google Maps, and it has become generally available. We have a research paper where we describe exactly how we've served it and the various considerations that we had to take into account. And it's globally available wherever you are in the world, England, France, anywhere in the world, this system will power your travel time prediction.
And is it still, so it's still this algorithm today? It's still the same one that you implemented?
So I wouldn't be able to tell you if the algorithm is different now because it's been a fair bit of time since I've last been in touch with this team. but I'm certain that the methodology is likely in spirit still the same. Likely there have been improvements on top of it, right? As Google gets better at routing for different kinds of objectives as well, right? So it's not always about fastest time, right? You might, for example, be okay with routing some amount of traffic on slower routes to kind of improve the overall congestion of the entire network, or to kind of reduce toxic emissions from cars. You might recommend to some people to take a bicycle as a first option. So basically, the system has gained a lot more of those kinds of modalities since then. But at the heart of it will still be a graph method.
And you mentioned classification, like it is the right classification. Is it not a regression problem? Like I would.
No, it is. It is a regression problem. So you are predicting travel time in seconds. I think is the unit that we're predicting in. Yeah.
Okay, but so by classification, maybe you meant you're within a certain threshold of the right answer, I guess.
So yeah, it can be. So one way in which you can measure the accuracy or the improvement is in kind of what is a negative user outcome. So how far away are you from the actual time it took to travel? And I think we took 10 minutes as a threshold there, but don't quote me on that. I'm not completely sure.
Okay, that makes sense. And maybe one last thing. So what was the most challenging part in this project? I guess from how you tell it, you replace the old algorithm with this new one, but I guess this is not as straightforward. So what was the biggest challenge? Was it to scale to 1 billion people, as you mentioned? Was it, I don't know, to train it? Was it inference? Yeah, what was the challenge?
I mean, I must stress that from my perspective, I did not perceive any huge challenges. I just, because my role was mainly a research one, right? So I helped the team kind of drive overarching decisions on specifics of the architecture, evaluating it under different scenarios, making sure that, we're not kind of collapsing to a trivial solution, qualitative analyses, things like that. So really what a researcher would do, right? There was under the hood a great deal of applied researchers at GDM who have kind of done the grunt work of actually coding this up and deploying it, and even extracting the representation in a format that a graph neural network would accept was an engineering effort unto itself. And then, of course, the fantastic effort from all the engineers on the map side to actually make sure that this clunky solution we've come up with can actually work in real time and serve users' requests. So it's like there were a lot of challenges, and we detail some of them inside the paper. A lot of them, just because of how well oiled the organization was in this regard, a lot of them were opaque to me. Like I was not aware of those challenges; they were not mine to solve. Right. So I did have research challenges, but to me, this was the same as if I was writing any paper, maybe with an additional twist that now I have to care more about latency than I normally would. So yeah.
Okay, we'll share the paper in the description then, in case our listeners want to learn more about that. Keen to dive on the last project. I'm a big football fan, support a bit more Tottenham than Liverpool, but keen to hear a bit more again about this project for Liverpool. How did you start collaborating with them? How did this idea of improving corner kicks came up? And then how did you use AI to solve this applied problem?
Right. So basically, it was I was not around in the team when the collaboration kick started, because our most recent paper, Tactic AI, we worked on it for a couple of years, but really the collaboration with Liverpool spans the past 5 years or so.
Okay.
And it was kickstarted in a sort of serendipitous way. So Carl Toyles, who was the research director on our sports AI effort, he also had an affiliation with the University of Liverpool, where he was a professor. And he actually got in touch when he was based there with some of the folks at Liverpool Football Club who were involved in data and decision making. And it was actually these initial chats about how could AI be applied and deep learning, how it could be applied to what they're doing, which led to the inception of our collaboration. And I think it also helped that our CEO Demis is a big Liverpool fan. So generally speaking, it was a very nice collaboration to set up. But I would also add that like much less beyond fan affiliations, Liverpool is a really good partner for a project like this because they have been data driven longer than any club in the Premier League and probably any club in the world, as far as I'm aware. Like they have had a proper like research team for I think at least a decade, and the people working on these research teams are people with STEM PhDs from Cambridge, Harvard, and so on. So these were people who spoke the same language we did. We did not have to, find different ways to explain something or kind of phrase the research in different ways because we were talking to someone who's in sports. We were talking to, a person who has a PhD in physics. And one of the basic parts of our architecture was, geometric deep learning and equivariance. And I think these people knew what equivariance was better than we did. So from that perspective, it was a super enjoyable collaboration. But yeah, it started out in a very serendipitous manner like that. And sometimes the best collaborations happen like that anyway.
And so can you explain a bit the AI pipeline, like input, algorithm, output, and what's the applied problem that you're trying to solve?
Right. So maybe, I realized I also haven't answered how did we come about to work on corners, and I think the pipeline will help explain that. So our main target was to build a system that can actually usefully influence tactical decisions. So this is the important part, useful, right? It wasn't let's train a machine learning system X and show that it's better than a machine learning system Y, and it just happens to be a football-oriented data set. We did not want to do that. Like there were like many papers trying to do this already, and because we had access to such a direct collaborator that's involved in such an important league, we thought it would make a better use of our collaboration to see are any of these tools actually having potential to be useful, right? And it was actually that constraint, the usefulness constraint, that drove us to corner kicks, because the system we built, I'll describe more about the system in a moment. It initially started out as a open play predictor. So we actually looked at situations when the game is not in a set piece situation, but just open football play. And I think our collaborators found those results pretty interesting. But they immediately told us, if you want to make this useful, you really should be focusing it on corners. And I think it makes intuitive sense to anyone who's watched football, right? Like you might have a system that detects certain things are not going your way in the moment, but how do you communicate that to the players without confusing the hell out of them, right? It's not easy. And I'm not saying it's impossible, but it certainly is not easy. Whereas corner kicks, on the other hand, and similar set pieces, have this great benefit of the game being effectively frozen, and corners have an extra benefit of the game always happens from the same position, which is a corner of the pitch. And unlike a penalty kick, it is a lot more frequent, right? And it gives you an immediate goal scoring opportunity. So corner kicks are really this great sweet spot that encompasses all of these qualities and makes it a really perfect candidate. In fact, I don't know if you've seen the movie Moneyball. If you haven't, and if some of your listeners haven't, I highly recommend it. It is, first of all, a very well-made movie, but it's a movie that deals with applications of statistical methods in baseball, right? And baseball is like a prototypical sport where you can apply methods like this very effectively because every single action in baseball is a set piece. Like the game is always frozen effectively with like brief action between plays, right? So corner kicks is the closest you can get to baseball inside the game of football with it actually being kind of an immediate scoring opportunity from a fixed position. Free kicks can also be dangerous like that, but you can't control where you're going to get fouled. So that was what brought us there, like the aim to be useful, right? So basically, the system takes as input the positions of different players on the pitch, which we can get through various sensors attached to their jerseys. You can also extract it from video data, whatever is more convenient. You take this data, you pass it through this geometric deep learning model, which is based on the graph neural networks we talked about before. And then you can predict a variety of things depending on what you care about in that situation. So you can try to predict who is going to make first contact with the ball, whether or not there will be a shot, whether or not there will be a goal. So these kinds of predictive modeling questions. These can be useful to coaches because you can try arranging players in different ways and seeing what happens to the predictions of the model. Then we can also use the model for retrieval, because if a model has learned to be really good at these kinds of questions, it has arguably learned representations of players that are important for predicting these kinds of things.
Mm-hmm.
So we could try to mine similar corners by checking which two corners are closest in this high dimensional feature space. And this is actually helping automate a task that human video analysts have to do a lot. Like, as part of preparing a strategy for the next game they're playing, a video analyst will look at a particular corner kick situation, and then they'll have to kind of look through many corners that a particular team has played to kind of figure out what the patterns are, how to best prepare, right? So if they have a system like this that can sort of hint to them what are the next videos they should watch given a particular video, this can obviously speed up their work a whole lot. And we found that using the Tactic AI embeddings, you actually get a much better retrieval recall than if you use some more simple heuristic like just proximity of XY coordinates. So that's pretty useful. It kind of learns tactically meaningful features. And lastly, we have the generative model, which given a specific corner kick situation, modifies the coordinates and velocities of players, either on the attacking team or the defending team, to maximize or minimize the probability of some outcome. So, for example, you can, if you're a defending team, you might want to minimize the probability there will be a shot, right? So the system will change the positions of players, change the way they're running, such that these things are they're better positioned to defend against that particular corner. And I must stress that this particular predictor is, like, its main use is not to come up with new tactics, because it's actually trained as a so-called variational autoencoder. So it's actually not trained to adjust the strategy; it's trained to reconstruct. So by definition, it will give you small changes to where the players are. However, those small changes, first of all, they're seen as significant by the coaches that we've shown them to, and also they just allow you to immediately focus your attention on which players might be doing a good job, which players might not be doing a good job. If these players are on your team, you need to coach them better. If they're on the opposing team, you need to kind of exploit that, right? So that's kind of the idea. And normally a coach has to look at 22 players' movements simultaneously and make sense of that. And it's not particularly easy to do it quickly. Here now you have a system that you just feed a situation into it. It spits out, adjusted positions and velocities. You can kind of immediately visually see what are the players that are being changed the most and whether it's useful or not. So anyway, those are the main outputs of the system.
Because on the third use case, so if you've got a player where the generative algorithm says, okay, this player doesn't have to move much, this means that this player is well placed and is doing well. Whereas if there is another player where the generative algorithm says, okay, this player has to move a lot to maximize the probability of having a kick or whatever, then it means that this player the position isn't great and has to be improved.
Yes, and we have actually good examples of this in the paper. Like, we've highlighted some specific corners in the Premier League and the outputs of our system for them. And you can see there's some situations where the whole defending team is doing a terrible job and all 11 players are receiving significant adjustments.
Yeah.
10, because the corner kick taker is not, but the others are. But then you also have situations where most players don't move that much, and there's like 2 or 3 players that are being adjusted, and that allows you to kind of zone in on it a lot more. So it's exactly like you say. It kind of helps you really narrow down who is critical by looking at these kinds of adjustments.
Okay, so if I recap, like 3 use cases, there is the generative one that we just discussed. There is the embedding one, where you can find similar situations for the video, for people who are analyzing videos. Is that right?
Yeah, retrieval.
And the third one is predictive, where you predict who is going to get the ball or whatever.
Yes, those 3.
And the third one, how does it work? Like, you get a situation, and before the corner, you just predict who is going to get the ball.
So the input is exactly the snapshot of the players at the moment the ball is being kicked. So you know for every player where they are and how fast they're going. That's the inputs you have. You also know for each player some simple physical attributes like height and weight. Those are the data we could easily extract from the Premier League data all the clubs have access to. In reality, different clubs will track different features for different players, and they might obviously train classifiers that advantage those features in different ways. So, we just wanted to see what is possible with a fairly simple set of features. But in reality, you can put a wide variety of things inside the nodes.
And why is this one useful? Like how can this be applied? Like you would analyze a screenshot. I mean, a screenshot of, let's say, the point where the corner is kicked, and say this person has a high probability of getting the ball. But how is that useful to Liverpool or to a football team?
I mean, first of all, remember what we talked about with retrieval. To get a good retrieval model,
Yeah.
you need a good representation. So to train on these tasks is how you build those representations in the first place. Second of all, you can do adjustments. So one thing that coaches always do is they will play around with where to put the players on the pitch. So you can, for example, imagine, just having a heat map, right, of where to put the player and how it adjusts shot probability. You can also imagine doing more crazy stuff, right? For example, you can take a player vector of one player and swap it with a player vector of another. And then you get an immediate assessment of, should I substitute this player? Or should we purchase a player if it's from a different team, right? So you can imagine this can be, like, the predictive model can be directly applied to drive those kinds of decisions potentially. But in the context of our study with Liverpool, the utility of the predictive model was mainly to create good representations for the retrieval model, which was a more immediate kind of application that they could have used it for.
And so, is it the same model for the tree applications? Is it a GraphML model, or you've got different models?
So it's the same model, just trained differently. So for the predictive model, we use just direct supervised loss on the outcomes from the games that we have access to. Retrieval is not trained. The retrieval just uses the representations for the first one. And for the generative, we use variational autoencoders, as I mentioned. Yeah.
Okay, super cool use case, actually. Very, big football fan, so it's nice to see that. And maybe one last question actually on that. Why GraphML? Why would you use a GraphML rather than another algorithm?
So in this case, you have kind of well-defined objects. There is a collection of players. There's 22 of them. There's also the ball if you want to model the ball as well. And very often outcomes in these different situations will depend on synergies between different players. So players that like to pass the ball around, a defender that particularly is good at tackling a particular attacker. So GraphML basically pushes the model to not necessarily extract all of those relationships, but drive its answer as a function of these pairwise interactions. So it kind of bakes in the prior that you're expecting the relationships between the players to play a good part. And I should stress that this is generally a really powerful paradigm, because under the hood, transformers and large language models are also instances of graph machine learning, because if you think about it, you have tokens, and different tokens are looking at different tokens and attending over the best ones. You're basically modeling pairwise interactions between tokens. The main difference between what happens in language and what happens in football is that words as well, but tokens especially, are meaningless, right? Like, you only get meaning when you combine it with what's around it, right? And attention, a really simple kind of direct sum of representations, is a very nice way to get meaning out of combinations of meaningless things, right? Whereas here we have players, they have well-defined positions, velocities, physical attributes. So the nodes in our graph are a lot better, I guess, formed than a simple token. And as a result, we can kind of exploit the graph message passing mechanism a bit more explicitly. So I would say that's the main difference. That's the main reason why we go for a graph system, but also it's remarkably general. Like, this idea of modeling pairwise interactions, basically all of our top tier models use this idea in one way or another.
Great. So let's finish the episode with just one career question. If you had one advice for people to progress in their career, what would it be? Just one advice.
So this advice might be a little bit biased towards my recent experiences and also people from the region where I'm originally from. So I'm originally from Belgrade in Serbia. I talk a lot to the local AI community there. We recently held a Eastern European Machine Learning Summer School in Novi Sad in Serbia. So I've had a lot of chances to interact with various stakeholders in the country. One thing I notice, and I don't think it only happens in our parts of the world. I think it happens everywhere, but maybe it's more pronounced there. One thing I noticed is that there is this level of, there's certainly no lack of talent. And I'm sure most of the people, or all of the people listening to you right now, listening to us, are very talented in something and could succeed if they wanted to and they put their mind to it. But one thing that was really missing for a lot of the people I've spoken to is, I wouldn't even call it initiative, but just confidence. Like being able to put faith in their abilities and actually, reach out to someone to discuss something, even if you don't necessarily feel like you are their equal at this particular point in time. So, reaching out, if you want to do kind of a research internship with a professor, reaching out to that professor, even if they are, the best in their field or, Turing Award winner or something like this, right? So, just having that confidence, if you want to work with someone or you want to discuss something with someone, just reach out to them, send them an email, and get to the point, ask what you want, and get opportunities this way. Because we have there's a lot of sensation that even though we're very talented, that these opportunities don't belong to us, and that mentality is what slows us down. So, like and we discussed this at the beginning of our talk, like some of the most important things that I have done in my career have started by me cold emailing someone or reaching out to someone I've never spoken to before, right? So I would say, if you are passionate about what somebody is doing, if you want to learn from them, if you want to, grow as a researcher, as an engineer, as a person, and somebody's help would benefit you there, somebody's insights would benefit you there, reach out to them. Like, you miss 100% of the shots you don't take. So just try it, keep growing, and I think that's a simple recipe to achieving any kind of success that you want.
Yeah, definitely agree. And I think there is also a part about like failing. Maybe people don't want to send this cold email or send this message because they're scared of getting a no and they don't want to get that no. But if you, as you mentioned, like, yeah, if you don't try, you're never going to get it. And so, there is this confidence bit that's super important, because if you're not confident, you're not going to do it. But there is also this, people are scared of failing, and you shouldn't, because that's how you progress. And if you never fail, if you never get a no, then you're not going to progress. You're going to get lots of no's, but you're going to get some yes as well. And
I mean, if you never fail, you have failed, right? Like, if you never fail because you never tried, you never succeeded, right?
Well, Petar, thanks a lot. It was great to have you on this show and learn from your experience. Have a great afternoon in the UK and hope to catch up soon.
Thanks again for having me. Great talking to you.
Thank you.